The third video in this lesson is to show you that the bases can be things other than nice numbers like we've looked at, 4 and 2 and any whole number. But I want to go back to a key concept I skipped over earlier. What is an exponential function and what are the restrictions on this exponential function form? First of all, here's the form of an exponential function. We talked about where the exponent had to be a variable. So this x is a variable and it can be any real number. So what we're saying is the exponent on this exponential equation can be any number that we want, positive, negative, real, it could be irrational, rational, anything we want. So that's the point. The other restrictions are a, the value of a cannot equal 0. If a was 0, anything times 0 is 0, so therefore you wouldn't even get much of a graph. It'd just be a flat line at 0, it'd be a constant graph. So we cannot allow a to be 0. And the other restriction that we have to pay attention to, b has to be positive. So far what I've told you is if the base b is greater than 1, you have a growth problem. And if b, or the base, is somewhere between 1 and 0, then you have an exponential decay problem. That still fits. I'm just going to point out to you and make sure that you're clear about an exponential function, what the values can be. X can be any real number, so the exponent can be anything. The base can only be positive numbers, but they can't be 1, and it also can't be 0, and also a can't be 0. So there are some restrictions and limitations. You should be aware of that. The point of this one is to show you that e, the base e, is one of the common and most common things that occur for bases of logarithms, or of exponents. And that's what it says here. It may surprise you to learn that for most real-world applications involving exponential functions, the most commonly used base is not 2, it's not 10, but it's an irrational number e, which we call the natural base. Now, e is defined to be the limit as x approaches infinity of this expression, 1 plus 1 over x raised to the x. So what they do in this reading here is they show you what happens as you let x get bigger and bigger, what happens to the value of this expression. This value of the expression gets closer and closer to a specific value. The specific value in more precision or more precise measure is here. It's 2.7, 1828, 1828. It continues on forever without repeating or repetition and without termination. So this number e, I kind of related a little bit to pi. It's an irrational number that's somewhat close to 3.14. E is an extremely important number when you look at limits and also in calculating compound growth or compound decay. Just as pi is an extremely important number when we start dealing with circles. Even though it's 3.14159, it's not a number that's we're real comfortable with. And as you've gotten more and more comfortable with 3.14 as you work through circles, you'll get the same kind of comfort feeling along with E. The more that you work with it, the more comfortable you'll be with it, the more that you recognize it, and it won't be such a strange number. But right now it's going to feel really uncomfortable, really strange, but E is the result of this expression raised to, or as x approaches infinity. That's what these value of E approaches. And it just occurs naturally in nature and as we do problems, and that's where it gets the term natural base. So E is the natural base. All we're going to do now is going to look at graphs of the natural base. So here's our first example that we're looking at. What I'm showing you is a graph of f of x equals e to the x. So here's really what we're saying. If we replace e with the decimal approximation, we're saying this is really like a 2.7. That's a real rough estimate raised to the x. And if we start looking at some ordered pairs, x and f of x, try our tried and true, -1, 0, and 1. Anything to the negative power means I've got to take the reciprocal of 1 over 2.7, so it's going to be 2.7 and 1 over 2.7, which is a fun thing to graph in and of itself. Next thing, if we put in a 0, 2.7 to the 0 power is 1, and 2.7 to the first power is 2.7. We can locate these points fairly quickly on the graph. If we put in the ordered pair 1, here's 1, we follow this up. Is it relatively close to 2.7? And most people would agree it would be. And also the ordered pair 0, 1 is on the graph. And then the one I didn't calculate very well, and I kind of drug my feet on because I didn't really want to do it, but I guess I will. What is 1 over 2.7 equivalent to? Let's clear that. I'm not giving you clearing action to go. So what is 1 Okay, we have a slight malfunction of that, which is not very much fun for me right now. So let's take 1 divided by 2.7, enter. Yeah, about a third. So not that it should have been any surprise. This is about 1/3 in the first place. I don't know why I didn't think of that. So -1 is about 1/3, and that seems reasonable from our graph. So this pink graph is nothing more than using a base of e, the natural base, which is a number that is very close to 2.7. So here we go again. What does this transformation do to it? What happened last time when we saw a negative put in for the exponent x? When we take and put in a negative value for x, this e to the x, this graph was e to the x, which is this graph in pink, then what is going to happen when we put in for our transformation, whatever we want to call it, r at x equals e to the negative x? So because that exponent is in grouping symbols, those implied grouping symbols, we're performing the opposite input. And when we put in the opposite input, it's a reflection across the y-axis. So all these ordered pairs that we have here, this 0, 1, fortunately that doesn't get turned around because it's already sitting on the y-axis. But the ordered pair 1.27, or this approximation, is going to get flipped to the other side. It's going to be -1, and at the same height, I'm going to try to put it in there. And then this ordered pair that's up here at 2, if you think about taking 2.7 raised to the second power, that's almost like a 2 raised to the third. That should be somewhat close to an 8. So up here close to the 8, we flip it around the y-axis or reflect it. It should be an 8. We take this ordered pair, which is 1 and a 1/3, -1 1/3. We reflect it. Now it's going to be 1 1/3. And we have our graph that comes along the x-axis, comes up through our 2 ordered pairs, or 3 ordered pairs we have graph. And we have a pretty good graph of this reflection across the y-axis. So again, this is the same thing that they did in the previous one, only we're using a base e. And just to show you that it shouldn't be too far off the mark, that's what that looked like if I use the graphing calculator or the computer image. Okay, second one, without using technology, how does this graph look? What kind of transformation is made? Well, this is going to be a little bit of a problem here, so I'm going to have to go back and grab a different graph, because I don't think I have it on here. I'm going to grab a different graph, come back, and I'll finish that so I have the right scaling on it. Okay, I'm back. What I did is I went and I noticed that this is a vertical translation. We got to move our graph 5 units downward. So in order to move it 5 units downward, I need a little bit more space. I went and grabbed a different set of axes. So we want to take this graph and we want to move it vertically 5 units down. And one of the things that is always important whenever you have a vertical shift, you want to take your horizontal asymptote and move it right away. We know our whole graph is getting shifted 5 units downward, so there it comes 5 units downward. Every point, and here's one of the big points you want to move down, the ordered pair 0, 1 gets moved 5 units downward. So if I move 5 units downward, it's going to be at 0, -4, and now I can sketch that graph. This was at -1 1/3, so we move it down 5 units. It's going to be at -1, -4, and yeah, whatever that is, that's not as much fun to move as I thought it would be. And then we move this one down 5 units down as well. So that was at 2.7-ish. So we move it down 5 units, it'll be at 3.7-ish. So we're going to scoop along here along the x-axis. We're going to come back up. At 1, we needed it to be at a negative. I forgot what I had there. This is 2.7. We want to move it down 5, so we want to go down to a negative 3.7. Let me try to make sure I got that right. Minus 2.7, moving it down 5, borrow, 10, 3, oh, how about a 2.3? Negative 2.3, so there's negative 2.3, swinging up through here. Okay, so using transformations to help us graph, somewhere in here I have this thing graphed as well, and you can see what the graph of that looked like if I just can locate it. Wherever it went, I'm not positive at this point, so I can't show you what the computer image of that one was. Oh, yes I can. Here it is. It got shifted clear up here. Oh, things are working smoothly today. And here's what that graph ended up looking like as we swing it down. So then I moved this, so really I've kind of got a mess going on here. That's what it's looking like. Still not quite right. Alright, so I got that a little discombobulated, but everything I did in there was okay. It's just that this is what the graph, we had to move that vertical or horizontal asymptote down 5 units and move every point down 5. That's the basic idea. Finally, we're going to switch back to what axis is going to work best for that. Get that one. I'm going to grab this axis again. We have a horizontal asymptote at y equals 0. Now, this one is going to be nothing more, and I'm looking at letter 3C as I'm moving stuff around here. 3C should be nothing more than a vertical stretch of our parent function, so all of our y values should get tripled. So if we need to, we can come back and say, all right, if our original function was, we'll put it in 2.7 raised to the x until we get a little bit more familiar with it. I'll get that lined up better. So this is 2.7 raised to the x. So if we put a -1, 0, and 1, so then our outputs were 1 over 2.7, which is about that third. We got a 1 for this, and we got a 2.7 for that one. In this transformation, we have to stretch it vertically, so we got to multiply all of these outcomes times 3. So we want to graph the ordered pair, -1, triple this, so it's going to be times 3. That's going to be awfully close to 1, because if you think of this as about a 1/3, you take it times the 3 over 1, we're going to be really close to 1. This one's going to be tripled, get to a 3, and 2.7 tripled, it's going to be awfully close to a 3 times 3 or 9, but we can get 21, carry the 2, that's 6, 8.1, so we're looking somewhere like that. Graphing these ordered pairs. I can put on a -1, 1, so -1 gets transformed to a 1. The 0, 3, so 0 comes up to a 3, and the 1 goes up to a 8.1, so it's going to go a little bit off of here, but you can see this vertical stretching. Now, whenever you have vertical stretches, they never change the location of your horizontal asymptote, so that's going to stay right where it is. So what you see is our graph being stretched and pulled away vertically. And I believe I have lost track of that one too. Here it is. That was this graph, and that's a pretty good replica of what I've already done. So this is a repeat of what we've already talked about. It is nothing more than transformations of the exponential graphs that we should be able to graph. This was just with base E. Remember, E is a natural base. It's about 2.7, 1828.